Hi, welcome. This is going to be a series of lectures on dual spaces in linear algebra. Hopefully, I should be able to cover whatever I want to do in about 3 to 4 lectures, 4 videos. First two videos must be enough for a student of BSc. The following videos may be for master's level. Okay, because I know that many students have a problem with dual spaces. And let's go as usual. We'll go slow, try to understand. Okay, you will follow it easily. Okay, let us get started. Yeah, before I sign off, usually I give references, and I'm not giving any reference for this series of lectures. If I can find something better, I'll come back and add it later in the videos. But at present, even in my book, I think linear algebra, a geometric approach, it's meant for BSc. So I had a very cursory uh, introduction to dual spaces. Okay, so I am going to rewrite if at all I want to do. Well, let us see. So let us get started. Before we start, yeah, this is me. This is the channel, YouTube channel, Kumar HSU, and please send any kind of comments, suggestions, or if you are pointing out some mistakes to this email ID, which is exclusively for my video lectures. Please do not write to my other email ID even if you happen to know that. Okay, and you may download the list of videos whatever is available on my channel from this site. Okay, just search for list of videos. The list gives descriptions, links of videos, and the videos are arranged in preferred order of viewing. It will also be periodically updated, and some of you, the viewers, had agreed to help me in this regard, so it will be easier for me. Okay, the updates will be announced through the post in my channel. So let us get started. So let V be a vector space over a field F. F is a field. Those who do not know, think of this F. These real numbers. That's good enough for us. Okay. Then all of you know what is meant by a linear map from F to. I will just write it arc F here. This is linear. Any linear map which is from the vector space to the ground field, this is called the ground field. This is called a linear form or linear function. In algebra they call it linear form. In analysis they will call it linear functional. Okay, right. So let us look at the linear maps. Okay, let us look at examples. V equal to, let us say, Rn. Okay, then we let E1, E2, En be the standard basis. I may write Rn as column vectors. Therefore my Ek will be 0, 0, 1, 0, 1 at the kth place. Therefore any vector x which is equal to x1, x2, xn is x1 e1 plus xn en. Since f is linear, suppose f is a linear map from Rn to R, then f of x will be f of x1 e1 plus xn en. By its linear map is additive, therefore it is f of x1 e1 plus f of xn en. But that's also equal to, since it's a linear, the scalars come out f of e1 plus xn f of en. Therefore if you let alpha I equal to f of ei, then you can see f of x is nothing other than summation alpha I xi I equal to 1 to n, where alpha is nothing other than f of ei. So we have found out any linear map linear functional f from Rn to R is of this form. Therefore, there exists vectors alpha 1 to alpha n, okay, such that, okay, f of x is summation alpha I xi. We also know what are alpha I, it is f of vi. Okay, right. And any such, take any scalars alpha 1 to alpha n in R and define f of x by this equation alpha kx k equal to 1 to n, then this is a linear function. So we had identified all linear functionals. Okay, therefore any linear functional Rn is of the form, let me call it f of alpha, okay, f of alpha, where f of alpha is defined by this equation. This is a row, as a row vector. Is that okay? So we have found out all linear functions, and notice that this can be done on any finite dimensional vector space V over a field F by choosing a basis, by fixing a basis V1, V2, Vn of V. And then write any vector V as summation xi vi, then f of x will be xi f of vi, that is equal to summation alpha xi, where alpha is f of vi. Right? Okay, pause, review. Proceed. I do not know why it's usually doesn't. Yeah, no, hopefully it doesn't do that. Let me just check. Okay, come back. Okay, PRP. So in particular, when n equal to 1, in the case of R, f of x is alpha times x, where alpha is f of 1, because the natural basis of R as a field over R is 1. Okay, right. Before we go further, let us introduce V star. Sometimes it's also denoted by V dash. It is called the dual space. What is this? This set of all linear functions f from V to the ground field f, where f is linear. So it is set of all linear functionals on V, on the vector space V. This is called a dual space. Okay, this is just a set. We want to call it a space because we are going to prove V star is a vector space. This more or less you must have seen, because whenever V and W are vector spaces, all the linear maps from V to W, this you know is a vector space. And dimension equal to dimension of V times dimension of W, if these are all finite dimensional. This you have seen this, right? So in particular, this is a vector space, but we will go through the proof in this case. So if f and g belong to V star, then I want to define f plus g. We have to define. How do I define? So this must be a linear map from V to f. That means I have to say what is its action at any point B here. So what we do? We define it to be, it is f of v plus g of v. Notice that f of v is a scalar, g of v is a scalar. In f we have addition, therefore this is. You understand this? Therefore this is addition. This, I have defined addition. Scalar multiplication. Suppose I have a scalar lambda in f, or let us say c a scalar in this, then c times f must again be a linear map from v to f, and c times f at a point b is c times f of v. Notice that f of v is in f, c is a scalar in f, therefore is a multiplication of scalars. Okay, so I leave it to you check. Okay, with this addition v star and plus this dot, let me write g dot. Okay, this becomes a vector space. You must have checked it in the, as I said, in this general case. Okay, this general case you must already checked it. Okay, but it will be worthwhile to do it again. Please check before you go further. Pause, review, proceed. Okay, right. So what we want to do is, this v star is a vector space. Notice that I have not assumed so far no assumption on dimension b. It may be finite dimensional or infinite dimensional. Okay, therefore v star is a vector space always. Okay, I don't require any assumption on the dimension. Okay, now what we want to do is, we want to do something else. Since it's, suppose v is finite dimensional, okay, then v star we want to find. So let us fix a basis v1, v2, vn of v, right? Okay, so I want to define f. Right. Let us just understand this. See, if f belongs to this, right, I want to define a basis of v star to find a basis, right? So if f belongs to this, notice that f of v, if I know f of vi, vk, okay, for all k less than or equal to n, then I know v. If we know this, we know the f, right? Because any linear map is determined by its action on a basis, right? So this suggests something like the following. Okay, so let us do that. This, if you notice, this is what we did in this case also here. Okay, we chose a basis of Rn and then we looked at it and then we are able to find all the bases, right? So that suggests something. Okay, so consider fi in v star defined by fi at vj is delta ij, that is equal to 1 if I equal to j, equal to 0 if I is not equal to j. This is called Kronecker delta. Okay, right. So notice that fi is defined only on the basis. This is for every one j less than or equal to n, right? Now how do I define on any v? V I will define summation. Suppose v is summation xi vi, then f of fi of x j vj, j equal to 1 to n, then fi of v is going to be, how do I define it? I define it to be simply fi summation acting on xj vj, which is going to be xj f of vj fi of. Okay, notice that this is going to be only xi. Okay, so this base, I want to say that fi I less than or equal to 1 to n is a basis for v star. Okay, how do I prove that? There are two things I want to prove. Okay, first I say fi 1 less than or equal to I less than or equal to n spans v star and it's a linearly independent. So I prove both the things. Okay, then that will become a basis. Is that clear? If this becomes a basis, this basis is called a dual basis. So how is the dual basis defined? Let us recall, it is fi acting on vj is delta ij. That is, fi act vi is 1, at all other basic vectors it is 0. Okay, pause, review, proceed. Let us prove that it spans. Suppose f belongs to v star, right? I think this color doesn't look nice. F belongs to v star. Then let us look at f. I want to define. So how do I define? I want to say it's a linear combination. I want to say f is a linear combination of some ci vi I equal to 1 to n. Okay, I want to write it. I want to show that this spans, that means any f is a linear combination, fi. Okay, ci fi, right? So our idea is to find ci's. Do you understand this? Yeah. If these two linear maps, this is a linear map, this is also linear map, they have to be equal. What do I know? Yeah, okay, they are equal if and only if at each j they agree on a basis. Therefore at each jth basic vector it should be equal to summation ci vi acting on vj, right? This happens if only this happens, right? Sorry, I write fi. Okay, but what is this? Remember, if f and g are linear, f plus g at v is f of v plus g of v. That's how we define addition of linear map. Therefore this is going to be ci fi acting on vj and summation over I equal to 1 to j equal to 1 to n, I equal to 1 to n, right? But what do I know this? This is fi, therefore this is delta ij, therefore this thing is 0 unless my I happens to be j. In that case I have only cj. Do you understand this? Okay, so what I have done? I have done that. I know how to write f as a summation. This is ck fk k equal to 1 to n, where I know what is ck now. It is nothing other than fk at k. Yeah, you understand that? Cj is nothing other than f at vk and fk. Note what does that mean? Ck is nothing other than f at vk, so I am writing this. Are you following? Yeah. So we just found it out. So let's go back. What I have done, I want to say this spans v star. Okay, so I am working backwards. Suppose it spans v star, then f must be of this form. And these two sides are linear maps. If they are linear maps, they are equal if and only if they agree on a basis. So let me work out on the basis, given basis b. Okay, for each j, f of bj must be equal to this. Then I found f of bj is nothing other than cj. That means I found the coefficient. See, we worked backwards. But in textbook, how will you do? Okay, to prove one, consider. Okay, given f in v star, consider. Okay, summation f of bk fk k equal to 1 to n. This is in v star, right? And we claim f equal to summation f of bk fk k equal to 1 to n. Okay, and this is true if and only if at each vi f of vi must be equal to, for all I, this must be equal to 1 to n f of bk fk at vi. I have to check. But this I know is nothing other than Okay, this remember this is k equal to 1 to n, and I is fixed. Therefore, this is equal to this if and only if my k happens to be I. In that case, is f of vi, right? Therefore, f at vi is same as this at vi. So I checked it, right? So it becomes a trivial verification, but what we did was we found out how to write this. Notice that this is exactly the same way we did even in the case of Rn. Yeah, what is alpha k? It is f at the basic vector. You understood that? Here also this is what we did. Okay, so please pause, review, and proceed. Next thing is I want to say linearly independent. Right? Suppose I have ck fk k equal to 1 to n is 0, and where ck's are in the ground field, then I want to know that it implies ck's are 0 for all k, right? Okay, but by now you should understand I want to show ck. How will I get ck? So it's enough if I show each ci is 0, right? So if I evaluate summation ck fk k equal to 1 to n at vi, what do I get? I get summation ck fk of vi k equal to 1 to n, therefore I get only ci. But this is 0. This is 0. 0 acting on vi is 0 linear map, therefore I get ci is 0. Right? This is a 0 linear map acting on vi is a 0 scalar. Okay, and this ck is a scalar. I got this scalar is zi, and for which I? For all I. Therefore, this is linearly independent. Right? So, pause, review, proceed. So, what have we shown now? Therefore, if V is finite dimensional, okay, then we have proved V star is finite dimensional, and in fact, right, dimension of V is same as dimension of V star. Okay. Okay. Right. Now, what we want to do is that we want to identify. First, let us notice that this is true only in the case of finite dimensional. In general, this is not true. What does it mean? If you know something about cardinality, etc., okay, if V is infinite dimensional, dimension of V may not be equal to dimension of V star. Okay, in infinite dimensional cases. But notice that both may be infinite, but then you need the notion of cardinality. This may be something like countable, this may be uncountable. We will give an example a little later, okay, but let's not worry about it at present. Okay, now let us look at one concrete example. The first thing one would like to talk about this is whenever you define a new space out of an old space, okay, you tried, for example, from V we found V star, right? The idea is to try to identify V star in a concrete way. What does it mean? That means try to show V star is isomorphic to some space, to some known space. Okay, So let me again try to understand what this means. Okay, see, B star is set of functions f from B to f, so that f is linear, right? So it is something like sub functions from B to f, and those functions are not all but only linear functions. Okay, but you would like to identify it in a concrete way. Let us look at a simple example. Okay, so this only means that I want to find an isomorphism. Okay, let us look at R. Okay, the same thing can be done on any F1 also. Okay, so as usual, I will write vectors as column vectors. Therefore, any x in Rn will be x1, xn, right? Okay, now see, notice that f, if in V star, that is Rn star, okay, then f is a linear map from Rn to R. Therefore, I can write down the matrix of f with respect to the ordered basis. What are they? Standard base E1, E2, N of Rn and 1 of R. Okay, and this matrix will be what size? It will be a matrix of size 1 size. Okay, again recall, if f is a linear map V to W, this of dimension n, this dimension m and dimension n, then choose a base V1 to Vm, W1 to Wn. Okay, the matrix of f with respect to these bases will be an n cross m size of this matrix. Okay, therefore this will be 1 cross n. Don't worry, we will do that. What does that mean? It only says, see, if it is 1 cross n, what does it mean? Okay, how will I do that? Let us recall that again. F of ei. Okay, we have to look at what is f of ei. Okay, that will be a number called bit alpha I. Okay, this must be the first column, ith column, right? Matrix of f with respect to the basis E1, E2, En, and with respect to basis 1 will be, the first column will be f of E1, which is alpha 1, and f of En, which is alpha n. Okay, again let us recall here. See, if you have learned those things well, okay, we can save a lot more time. Okay, we write f of vi as a linear combination of a, j, I, w, j, j equal to 1 to n. This forms the ith column, that is aj, a1i, a2i, a-ni. Okay, this is how the matrix is written. Okay, therefore this is matrix. But this is what? This is a vector in Rn, but in Rn now the vectors is considered as row. If you want here, I can think of the Rm as column. Okay, therefore any f is identified with alpha 1 to alpha n, which is Rn row. Because we had already seen any f is determined completely by these scalars, right? Therefore there is a one-to-one correspondence with this. Therefore, in other words, what you have done is, let us look at Rn column, and its dual is nothing other than meaning isomorphic to Rn row. That is Rn consisting of row vectors. Okay, please think about it. It may take little time, but you should be able to do that. Okay, so pause, review, proceed. So this is what we mean by we are describing V star in a congruent way. That is, we are saying V star is isomorphic to a known space. What is the known space? I look at Rn of column vectors. Okay, this dual is Rn which consists of row vectors. And how is the correspondence given? So any f in Rn column star is associated to alpha where in Rn row where alpha k is f of vk, and also f of v, f of summation xi vi 1 to n is nothing other than f of alpha I vi, alpha xi, sorry, f of vi will be alpha xi. This is a number. You understand? Don't get worried. You will see in modern mathematics, whenever we have an object, we construct new objects out of that. For example, you would have already seen V and W are vector spaces. We have external direction, B direction down W, and G and K are groups. Then G cross K, Cartesian product can be given a direct product of groups. So we construct a new thing. Okay, in some of the cases, we may want to identify them in a concrete way. Okay, even quotients things you will do that. Okay, here what we have done is given a vector space V, okay, namely Rn, which is consisting of column vectors. Okay, we know Rn star, that is the dual of that. It is set of all linear functions from Rn to R. Okay, but what we say is that it is same as isomorphic to the row vectors in Rn. Okay, where Rn is considered as row vectors. This is the way. Okay, think about, get used to this way of thinking. You will find it is much easier. Okay, let us look at some more examples. Now suppose one more example. Suppose I have an n cross n matrix of real. Okay, and I want either a linear function from Mn or to R. I want to find this thing. Okay, first notice that we know that M and R is isomorphic to Rn squared. How do I do that? If I write A equal to A11, A1n, AN1, ANn, I map it to A11, A1n, A21, A2n, AN1, ANn. This is the Rn squared. Right? This is a linear isomorphism. Right? Therefore, we know any linear map F from M and R to R, that is linear functional or linear form. Okay, should be of the form summation sum alpha ij aij summation over I and j, not j and I, where alpha ij is f of some basic vector, ijth basic vector. Right? So what is the basis? Right? This again you might have seen. Look at the matrix Eij, which is okay, ith column, ith row, and jth column 1, all other places 0. Right? And that is Eij. Let us look at Rs, that's Rs entry of this matrix, okay, is equal to 1 if I equal to R equal to I, and S equal to J, and 0 otherwise. because I want to say R is entry, therefore I have to put condition on R, which that is R equal to I. Yes, and put condition on yes, which must be J. So only at ijth place is 1, at all other places 0. Do you understand that? Therefore any matrix A now is nothing other than Aij, Eij and J and I. Do you understand this? You might already seen this. Okay, pause, review, proceed. Okay, now the question arises, can I, we had already identified, but then since we are dealing with matrices, okay, I would like to any linear map in terms of matrix operation concepts related to matrices, right? Please understand, these are the things which will be slightly above if you are a BSc student, but try to understand. So what did I do? I want to find all linear maps from MNR to R. So what did I say? Okay, I simply said MNR is as good as Rn squared with respect to this mapping. Therefore any linear function from that should be of the form summation over I, summation over j of alpha ij, aij, where alpha ij's are scalars. And what should be alpha ij? From whatever we did earlier, fix a basis for MNR and f should be expressed in that. Okay, and what is the basis we are choosing? The base we are choosing is Aij. With respect to this basis, okay, then we found out my capital A is summation this, therefore I found out this. Okay, but this linear map I described in terms of the isomorphism of MNR with Rn squared. Oh, I forgot to screen share as usual. I do not know where I did. Yeah, let's go back. So I want a MNR n cross n square matrices and linear map. Then you identify MNR with Rn squared, and for basis for MNR is Aij, where 1 at ith entry, otherwise 0. Okay, then write A equal to summation Aij, Eij, then operate f on that, then we get f of A must be alpha ij, aij. Okay, so we got it. What I said was, this description of a linear function on MNR involves the way I identified MNR with Rn squared. Okay, the linear isomorphism. Okay, whereas I would like to do intrinsically. One says intrinsic description. Okay, so BSc students, if you find it little overwhelming, you can stop here, okay, and leave the video, right? But those who are interested to learn much in depth should go forward. Okay, what we plan to do is, let's look at something. Okay, so now let us look at the same thing. Okay, Eij. Suppose f of Eij I denote it by, let us say, b of gi. This is my notation. Find bji by f of Eij. Okay, then I get a matrix B, which is bji. Okay, again 1 I j less than or equal to n. Right, this is a matrix. You understand that? Now let's look at, in terms of this matrix, let us look at f of A. F of A is nothing other than f of Aij into Aij. Right? This summation over j, summation over I. But what is this? This is I and this is over j. This is b j I and Aij Therefore this is nothing other than sum of diagonal entries are the product matrix BA. Do you understand this? Yeah. Therefore that is nothing other than this is that has a name. This is trace of BA. Now do you see that we defined everything in terms of matrices? What did we do? So given F, I define a matrix B. Matrix B is B of F of E J I. Okay, this is the matrix. Then what did I find? F of A is nothing other than trace of B times A. Now B times A is a matrix product, and trace of matrices, square matrices, somehow diagonal entries. Therefore any thing I define. Okay, therefore any given if F from M and R to R is linear, then there exists a B in M and R such that F of A is trace of BA. Okay, pause, review, proceed. So we identified any linear map, and we want to say now fix any B in M and R, define F of B at A to be trace of BA. Is this linear? That is very easy. Notice that FB of A1 plus A2 is trace of B times A1 plus A2, and matrix product is distributive, therefore B of A1 plus B of A2, and trace is additive, therefore trace of BA1 plus trace of BA2, but that is F of A1 plus F of A2. Similarly, FB of C times A is C times FB of A. So what I have shown, therefore the main result we have shown is F from M and R to R is linear if and only if there exists a B in M and R such that F of A is trace BA. Yeah, right. Now before I stop, pause, review, proceed. So let us understand the dual basis again. Okay, so notice that what is the meaning of dual basis? Fi, let us look at an Rn. So let me look at Rn with the column and Fi. Okay, Fi of Vj is delta Ij. Therefore what is Fi? Fi of any vector x is going to be Fi of x1 e1 plus x1 en. Therefore it is going to be xi. Therefore you can see Fi, the dual basis is ith coordinate functions. Therefore any vector, any v in Rn column can be written as v equal to summation Fi of v into Ei. Do you understand this? More generally, V is finite dimensional, V1 to Vn is basis, and V star we know it's finite dimensional, and let us look at f1 to fn. It's a dual basis. Then any vector v in V I can write as uniquely fi of v into vi. How many of you understand this? Okay, is that clear to you? Because right, suppose I know this is xi vi I equal to 1 to n, right? Now I want to know what is xi, right? I am claiming it is nothing other than fi of v. How do I do that? Okay, let me write xk of vk. Therefore, what is xi? Let me write fi of v. Then it's going to be fi of xk vk k equal to 1 to n. That is going to be summation xk into fi of vk k equal to 1 to n. And this survives only if k equal to I. Therefore, I get xi. You understand that? Therefore, we proved this result. Yeah. Pause. Review. Proceed. Okay. Now tomorrow we shall look at, in the next lecture, we will look at some more examples about dual basis. Okay. Therefore, what is the dual basis for Rn with column vectors? If you want to think of it differently, okay, then it is standard basis e1, e2, en. Okay, my f1 is the row vector 0, 0, 1 at 0, 0. This is ith place. Okay, this is the, therefore this f1, f2, fn is a dual basis. Please go through that. I know that many BSc students may struggle, but revise this with your friends. Okay, and I am showing how many different ways one can think of the same concept. This kind of thing, if you learn much earlier, you will see that you will be much more comfortable. And go through those things. We will look at it a little more, few more examples in the next lecture. Okay, stay tuned, take care, stay safe. We'll meet again.